Okay, so good morning. Today we're going to have a online or recorded lecture for signal spectra and signal processing. So because today we have a lot of meetings and other activities at the university, so in this way we could have to supply you with an alternative learning way discuss our subject. So last weeks we are already on lesson 4. So we discussed already the signals and its characteristics, sampling theorem and aliasing. Now we are going to move forward for the filter difference equations. So these are more on the mathematics on signals. So these are the future topics that we're going to discuss. So for lesson 4, so we're going to consider discrete time signal as well as Fourier analysis. We will not touch up convolution and correlation because that is would be on lesson 5 and 6. So as a outline, so we have this following. So what is the discrete time signal? So discrete time signal is a index of real or complex numbers, and its discrete time signal is a function of integer valued variable n by the function of n. So inside x, so you could see these values. For example, you have x at 0, so we try to implement that x is 0 should be in positive or negative integer. So yeah, it's either -1 or it's going to be 2 or it's going to be 3. So what is discrete time signal? So an example of this can be derived from continuous time signals such as speech. And how do you record speech? Through microphone, you could be able to transfer signal from analog to digital converter. So digital converter that we will be transferred to a computer or a chip, and this continuous time signal is being sampled at a rate of that is in frequency, that is 1 over t, and t is your period, or that is in second, and your f is in frequency. So but in this given this example, it would be called as samples per second, which produces sampled signal x sub n, and which is related to x sub a function of t as follows. So this is the function of n equals to x sub a to n multiplied to the period. That would be the function for this signal. Some signals may be considered to be naturally occurring in discrete time sequence because there is no physical analog to digital converter that is converting analog signal into a digital signal. Examples of the signals are, we have stock market prices, population statistics, warehouse inventories, and Wolfers-Sandpot's number. So we have one of the examples of a discrete time signal. So we have from famous astronomer Wolf Johann Rudolf Wolff is a Swiss astronomer and a mathematician best known for his research on sunspots. Wolff was born in Zurich and he studied at the universities of Vienna, Berlin, and in Switzerland. So he's one of the professor of astronomy at the University of Bern in 1844 and become a director of the observatory on 1847. So he accepted the chair of astronomy at both university and the Federal Institute of Technology in Zurich. So what is a Wolfel sunspot number? It was introduced by Rudolf Wolff in 1848. It means that it's going to estimate the measure of sunspot activity using daily records that is dating back to 1818, and it would estimate monthly means have made in 1849. So this is one of the useful use of Discrete-time signal. So consider in general, discrete-time signal may be complex valued. So in fact, a number in the important applications is such as digital communication. Complex arises naturally in a given imaginary parts. So you have n added to j b function of n. So in this value, you could relate these two as real and imaginary parts. And in other forms, you could have it in polar form using the magnitude and the phase, using the exponential value and the what called absolute value of Zn. So that is for complex sequences. How do we implement complex sequences is from the derivation of real and imaginary parts. So we use Pythagorean theorem, and in this case we could generate this value. So you have the R Z and you have the uh, negative tangent, imaginary over real. So the complex sequence is a complex conjugate denoted by Z uh, asterisk n, formed by changing the sign on the imaginary part. So we have the formula Z to the asterisk n, and we have the real and imaginary number or the imaginary part of the equation. For some fundamental sequences, so we have example of unit step. So in this example, we have at -1. So n will be equal to 0 if the value of the unit sample is at 0. So it would be other value. For unit step, so we have this example. So at 1, n is greater than or equal to 0. If the value is 0, uh, it would be other values. So, and this equation is related to unit sample by u function of n, that is in the summation of n to the unit sample. In this way, the difference equations of the two steps may be implemented in the unit sample as unit step minus u to the n minus 1. So also we have exponential sequence equations. So there is a that may be a real or complex number that is x n as function of x, function of n using n as a function of x, and this would allow us to have a that is raised to the n, where the exponential sequence is formed when a is equals to the exponential of j uh, uh, w sub 0, where w sub 0 is a real number and x function of n is a complex polynomial. So in this way, we could generate another equation. So we have exponential to the j and a, we have the w sub 0. So we have cosine n w sub 0 plus j sine n w sub 0. So this is an example of your exponential sequence, and that can be used in a Fourier decomposition of signal. For finite length sequence, it is equal to 0 for all values of n outside the finite interval, that is n sub 1 to the, also we have n sub 2. So the signals finite in length, such as the unit step and the complex exponential as we discussed before, are said to be infinite length sequences, may be further be classified as either right-sided, left-sided, or two-sided. Right-sided sequence in an any infinite length sequence that is equal to 0 for all values of n that is less than n sub 0 for some integer that is n sub 0. So the unit step of the right-sided sequence is also an infinite length sequence, are said to be left-sided. So n sub 0 is equal, should n function x sub function of n equal to 0 for all values of n greater than n sub 0. So an example of left-sided sequence is that we have this. So x function of n equals to u, that is open inside the function of n sub 0 minus n equals to 1, which n should be less than or equal to n sub 0, and you have 0, and greater than n sub 0. So this is a time reversed and delayed unit step. So this is another type of equation that can be used for signal duration. Now, we have also the two properties. Sorry for the other one because it was covered by the video. So in this way, a signal is said to be periodic, as we discussed earlier examples. For some positive real integer n for all small n, this is equivalent to the sequence repeats itself every n samples. So if a signal is periodic with a period n, it also periodic with 2 to the n, and periodic with 3n, and all other integer multiples of n. So this is what we call a fundamental period, in which we denoted by the big letter n. The smallest possible positive number of the integer for integer is satisfied, and for the previous equation is not satisfied by the integer n is said to be a periodic. So if this is not periodic, it is not satisfied based on the equation that we have. So a signal x sub 1 function of n is periodic with a big letter n sub 1 and x sub 2. Function of n is another sequence that is periodic with a period big letter n sub 2 is equal to the sum, that is the sum of the two signals. This is the equation for the sum of the two signals that is periodic. And we have the fundamental period product equation. So this is how we have the multiplication and addition for our periodic signal. Now for our real valued signal is even for all n if x is equal to x function of negative n, and if it is odd, it's x function of n equals to negative x to the function of negative n. And this is also discussed in the previous examples we have in lesson 3, but this is on the symmetric sequences. So this is a review of what we discussed last time. So also we have a complex signal that is conjugate symmetric for all n. This is the equation. We have the conjugate antisymmetric for all n, that is also applying the same concept as the first one in even and odd. So this would allow us to see that we could apply in a signal in a that we could always decompose into sum of the conjugate symmetric and conjugate antisymmetric. So any signal may be decomposed into sum of its even part and its odd part. So this is one of the sculpture of Fourier. So he's Jean-Baptiste Joseph Fourier. So he's a French. He was a French mathematician, and physicist Born-Sauzer is known for investigation of Fourier series, which was eventually developed into Fourier analysis and harmonic analysis, and their application in various fields in heat transfer and other laws like Fourier law of conduction, and also used in Fourier transform. So why Fourier analysis? Because it provides a different way to interpret signals and systems, and its complex exponential are eigenfunctions of linear shape invariant systems. So our focus for discrete time signal is more on linear shape invariant systems. And also we have the property that leads to the notion of frequency response of the representation of LSI systems. So we have this basic Fourier analysis. So this is an example of the eigenfunction of the linear shift invariant systems and sequences that are when the input to the system pass through with only one change in complex amplitude. So this is the input x function of n that has an output of y function of n, that is lambda equals lambda multiplication to the x function of n, where lambda is the eigenvalue, generally depends on the input of x of n, x function of n. So the eigenfunction is uh, also, this could be attributed to as x is your input and h sub n with your process, and this is would be your output. So before we move forward with the Fourier analysis, so we will discuss first filter. So what is a filter? Filter is often used to as a discrete time sequence because the computational process or algorithm by which the sampled signal or sequence of numbers is transformed into a second sequence of numbers termed output signal. So filters can be classified based on their computational process. So we could have the four basic filter. We have the low pass filter that is based on the passband frequency that you allow only a low frequency to pass through in this type of filter. We have also the high pass filter, so you don't allow lower frequency to pass through, but you only allow uh, high frequency to go with your signal. So as you can see, the graph between low pass and high pass are uh, not intersected because they have a different notion of accepting frequency in the frequency domain. So we are not on the time domain in using filters. And we have also, second, we have the band pass filter. So when you say band pass, there is only a specific frequency. So as you can see in letter C, the frequency between are accepted, but the frequency before and after are neglected. So meaning at this point or in this range, the frequency are being allowed to pass through. Now for the fourth one, this is rarely used. We have band reject. So there is a specific frequency band that is being rejected when this type of filter being used. So the frequency before and after are being accepted, but the specific frequency on band reject will be not will be filtered. So this is more on specific frequency that is being filtered. So where can we apply this? So example, if you want to uh, reject frequency from a specific channel, so if we put the range of the channel, and this channel will not allow you to uh, get the information. So in this way, we could limit uh, the frequency band, or we limit the information that being transferred using band reject. Actually, low pass filter is mostly used specifically in logic circuit also. In your body, you have low pass filter in your nerves. So low pass filter always reject uh, 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 high or higher signal. It only allows lower uh, frequency to pass through, and high pass filter only allow high frequency signal. So that's the difference between the two. So we have equation from linear phase. So these are equation. If you can see, it's similar to the equation that what we have previously using real and complex numbers. So in this equation, you use a real number, and after it was applied, so you have called a generalized linear phase if you have this equation, and this would have a constant group delay in as a result. We have also all pass filter, so it allows all frequency response to pass through. So this is the equation for all pass filter. And for selecting filters, we have low pass, we have the high pass, and we have the band pass filter, and also we have what we call the band stop filter. So uh, these are the filter that can be used in system properties of your signal. So how do we implement discrete time systems? Is using linear shift invariant. So these are the properties because after this, it's going to be convolution also. So LSI system, if the response of the system to an impulse function is known, so the output of the system can be predicted for any input. So this is achieved through convolution process. So this is the equation, represents the impulse response of the system. You have the analysis of LSI system usually becomes easier if Fourier transform function is used. So that's why the final equation, so this convolution can be replaced into G's function of u equals to f function of u as well as h function of u. So this is the equation. So the implementation of discrete time sequence is in Fourier transform as well as in the convolution. So these are the course sources for this lecture, and thank you for listening. Goodbye. So if you have any questions, please drop by your Neo LMS questions for the subject. Thank you.